So this is going to be a relatively short video just to give you a quick example of optimization with two constraint equations. So if you have a function of three variables, w equals f of x, y, z, subject to two constraints, this is possible to use the method of Lagrange multipliers to optimize it. So this time we have constraint equations g of x, y, z equals 0 and h of x, y equals 0. Each of those are surfaces in R3. So we have two surfaces as our constraint equations of a four-dimensional graph object, whatever. We can't really picture it with software because it's in 4 dimensions. Anyway, we will need to solve the system given below. Notice again, it's everything to do with gradients. So the gradient of f needs to equal lambda times the gradient of g, but then we're adding this new piece, plus mu times the gradient of h. Both lambda and mu are known as Lagrange multipliers in this case. The function we're going to work with is f of xyz equals xy plus yz, where x, y, and z are each non-negative, subject to two constraints, the first being x plus 2y equals 6, and the second being x minus 3z equals 0. So we will need to rewrite each of these constraints as functions of three variables. So the first one would be x plus 2y minus 6 equals 0, and the second one, h, would be x minus 3z equals 0. This allows us then to find the gradients. We'll find the gradient of f, the gradient of g, the gradient of h, as we have here, y, x plus c and y for f, 1, 2, 0 for g, and 1, 0, negative 3 for h. It's nice in this case that the gradients of g and h are both constant vectors. Now we're going to plug values into our Lagrange equation. So the partial derivative of f with respect to x needs to equal lambda times the partial derivative of g with respect to x plus mu times the partial derivative of h with respect to x. This is plugging in each of those values. So y equals lambda times 1 plus mu times 1. In the case of the y components, we have x plus z equals 2 times lambda plus 0 times mu. And in the case of the z components, we have y equals lambda times 0 minus 3 times mu. So we'll now have a system of 5 equations. And I'm going to remove this. 5 equations. Let's just call this the x gradient equation, the y gradient equation, the z gradient equation, and then our two constraint equations. So we have a system of 5 equations in 5 variables. If you work with the first 3 gradient equations, you can deduce that lambda is equal to negative 4 times mu. And if you want to pause and see if you can come to that conclusion just working with those 3, I encourage you to do so before resuming, because I've skipped a lot of the steps here. But I'm solving those using the first 3 equations to deduce that lambda equals negative 4u. And then if we take the lambda equals negative 4u and work with the second and the third gradient equations right here, you can conclude that 3x plus 3z equals 8y. And essentially at this point we have removed lambda and mu from the equation. We've taken the first 3 equations and been able to reduce them to 3 equations. So, let me say that better. The first 3 equations become this single equation, which will now combine with our last 2 equations to produce a system of 3 equations in 3 variables instead of a system of 5 equations in 5 variables. Lots of different ways you could choose to solve this equation: substitution, addition, elimination, graphically, however you'd like to approach it. If you solve this system, you arrive that the point 3/3 1 is the only solution to this system of three equations. We plug that point back into our original function f to find that f of this point is 6. And then you can test any other point around it to see that they are all lower than 6. And therefore 6 is a maximum as we desired. And that's the end of this video.